Hello there, and welcome to this quiet journey through the universe. Tonight, we are drifting toward objects so dark that they cannot be seen directly, yet so powerful that they shape stars, galaxies, light, and time itself. Black holes are often described as cosmic monsters, but that phrase is almost too simple. They are not empty mouths floating through space. They are places where gravity changes the meaning of distance, where clocks disagree, where light can orbit, and where the laws of nature begin to reveal their deepest unfinished questions. Some are only a few times more massive than the sun. Others hold the mass of billions of suns. Some sleep almost invisibly. Others shine through the matter around them more brightly than entire galaxies. So let your shoulders soften. Allow the noise of the day to move a little farther away. And as we explore 100 of the strangest and most mysterious facts about black holes, there is nothing you need to remember. You can simply listen, imagine, and drift. Let's begin. A black hole is not an empty tunnel in space. It is a huge amount of matter crushed into an extremely small region. Its gravity becomes so powerful that beyond a certain distance, even light can no longer escape. That invisible limit is called the event horizon. And quietly, another curious detail appears. The event horizon is the invisible border around a black hole. It is not a wall, a shell, or a physical surface that you could touch. Imagine a waterfall in a river. Before the edge, a boat may still turn back. But after crossing it, the current carries the boat only one way. Around a black hole, the event horizon is that point of no return. It surrounds the dark center, and anything that passes inside can no longer return to the outside universe. It may seem surprising at first. The dark circle in a black hole image is larger than the black hole's true point of no return border. It is a little like seeing the silhouette of an object in front of a bright fire. The darkness tells us where light failed to reach us. The black hole bends nearby light, and some light is trapped before it can reach us. This creates a wider, dark silhouette called the shadow. So the famous image does not show the black hole itself. It shows the darkness the black hole creates in the glowing material around it. You can picture it for a moment. Black holes can be quieter than empty space. A black hole with nothing nearby may emit almost no detectable light. The brilliant images we associate with black holes usually come from hot matter outside them, not from the black hole itself. And here, the picture becomes a little more unusual. The brightest objects can hide black holes. Quasars can outshine entire galaxies because gas falling toward a supermassive black hole becomes extraordinarily hot before crossing the horizon. The darkness at the center can power one of the brightest beacons in the universe. There is something quietly fascinating about this. Matter falling toward a black hole often gathers into a wide, spinning ring called an accretion disk. Think of an impossibly fast cosmic racetrack. Gas circles again and again, rubbing, colliding, and heating until it glows brighter than many stars. The gas races around, collides, and becomes extremely hot, much like metal glowing inside a furnace. Before any of it disappears, the disk can shine in ultraviolet light and X-rays at temperatures of millions of degrees. A black hole can feed without swallowing everything. Much of the material approaching a black hole never reaches the horizon. Magnetic fields, radiation, and turbulence can throw part of it back into space. For a moment, consider what that means. Jets can escape from beside the point of no return. The black hole itself stays dark, while the space around it behaves like a gigantic lighthouse, sending narrow beams far across the universe. Nothing escapes from inside the horizon, yet narrow jets can erupt from the region just outside it. Magnetic fields tap energy from the rotating disk and possibly from the spinning black hole itself. Some jets cross thousands of light years. The black hole itself stays dark, while the space around it behaves like a gigantic lighthouse, sending narrow beams far across the universe. A supermassive black hole can launch streams of particles far beyond its host galaxy's center. These jets can shape gas on scales larger than entire galaxies. And quietly, another curious detail appears. Black holes can regulate star formation. The black hole itself stays dark, while the space around it behaves like a gigantic lighthouse, sending narrow beams far across the universe. Energy from black hole jets and winds can heat or remove the cold gas needed to form stars. In other places, the same outflows may compress gas and help new stars begin. It may seem surprising at first. Most large galaxies appear to hide one. Observations indicate that nearly every large galaxy contains a massive black hole near its center. The black hole may be tiny compared with the galaxy, yet its history is closely connected to the galaxy's growth. You can picture it for a moment. Our galaxy has a 4 million solar mass black hole. Sagittarius, a star, sits at the center of the Milky Way. Its mass is about 4 million suns, compressed inside a region smaller than the orbit of Mercury. And here, the picture becomes a little more unusual. Sagittarius. A star changes in minutes. For a distant observer, a clock near the black hole would appear to slow, as though each second were being stretched longer and longer. Because the glowing region around our central black hole is compact, hot gas can orbit and change on very short timescales. The EHT had to reconstruct an image of a target that was shifting while it was being observed. There is something quietly fascinating about this. M87 star is billions of times more massive than the Sun. It is a little like seeing the silhouette of an object in front of a bright fire. The darkness tells us where light failed to reach us. The first black hole image revealed the shadow of M87 star, a giant of about 6.5 billion times the mass of the Sun. Its immense size made the horizon large enough to resolve despite its enormous distance. Two very different black holes look strangely alike. It is a little like seeing the silhouette of an object in front of a bright fire. The darkness tells us where light failed to reach us. 87 star is far more massive and farther away than Sagittarius, a star, yet their apparent sizes in the sky are similar. Einstein's theory of gravity predicts the same basic ring and shadow structure across that enormous difference in scale. For a moment, consider what that means. The first black hole image was created by linking radio telescopes in different parts of Earth. For a distant observer, a clock near the black hole would appear to slow, as though each second were being stretched longer and longer. Each telescope observed the same object at the same time. Scientists then combined the recordings as though the telescopes were pieces of one enormous dish, almost as wide as our planet. The famous orange ring is not an ordinary camera photograph. The telescopes recorded radio signals, and computers used those measurements to rebuild the most likely image. Several independent methods produced the same basic ring and dark center, giving scientists confidence that the structure was real. And quietly, another curious detail appears. Magnetic fields near a black hole behave like invisible, twisted ropes. The black hole itself stays dark, while the space around it behaves like a gigantic lighthouse, sending narrow beams far across the universe. They guide hot gas, slow some of it, and can help fling other material away in narrow jets. Special observations of the light reveal the direction of these hidden magnetic lines. It may seem surprising at first. A spinning black hole does more than rotate by itself. It also twists the space around it, a little like a spoon, turning inside thick honey and pulling the honey along. Very close to the black hole, everything is forced to move partly in the same direction as the spin. You can picture it for a moment. Around a spinning black hole is a zone called the ergosphere. Picture stirring a spoon through thick honey. Close to a spinning black hole, space is dragged around in a somewhat similar way, and nothing there can remain completely still. In this region, space is being dragged around so strongly that nothing can remain completely still. In theory, matter entering this zone could leave with some of the black hole's rotational energy, causing the black hole to spin slightly more slowly. And here, the picture becomes a little more unusual. A black hole can spin incredibly fast, but the equations suggest there is a maximum. Think of it as a critical speed limit. The more mass the black hole has, the more spin it can safely hold. Black holes created in nature are expected to remain just below that limit. There is something quietly fascinating about this. Time passes more slowly near a black hole because gravity affects clocks. For a distant observer, a clock near the black hole would appear to slow, as though each second were being stretched longer and longer. Imagine two identical clocks. One stays far away, while the other is lowered close to the black hole and later brought back. The clock that went near the black hole would show that less time had passed. From far away, we would never watch an object pass through the event horizon in a clear, final moment. It is easiest to imagine it as the edge of a waterfall. Before the edge, a boat may still escape. After it passes the drop, every possible route carries it farther down. Its light would become weaker, redder, and slower to arrive, making the object appear to fade near the edge. But for the falling object itself, the crossing would happen after a normal, limited amount of time. For a moment, consider what that means. Crossing the event horizon of a very large black hole might not feel dramatic at first. It is easiest to imagine it as the edge of a waterfall. Before the edge, a boat may still escape. After it passes the drop, every possible route carries it farther down. There is no wall to hit, and no alarm that announces the crossing. Because the change in gravity across a person's body could still be small there, the traveler might pass the boundary without noticing the exact instant. Smaller black holes can be more powerful near their edges. It is easiest to imagine it as the edge of a waterfall. Before the edge, a boat may still escape. After it passes the drop, every possible route carries it farther down. Close to them, gravity may be much stronger at a person's feet than at the head. That difference can stretch the body severely, even before the event horizon is crossed. And quietly, another curious detail appears. Scientists jokingly call this stretching spaghettification. It is the universe turning a solid object into a long thread, pulling much harder on the nearer end than on the farther one. The side of an object closer to the black hole is pulled more strongly than the side farther away, stretching it lengthwise while squeezing it from the sides. The name sounds playful, but the effect would be extremely destructive. It may seem surprising at first. At the center of the simplest black hole models lies something called a singularity. The word does not mean that scientists have photographed a tiny dot inside. It means our current equations reach a place where they can no longer tell the rest of the story. The equations describe matter and space becoming compressed without limit, producing impossible values. Most scientists do not think this is the final answer. They see it as a warning that our current theories stop working there. You can picture it for a moment. Inside a black hole, the center is not simply a place you can choose to avoid. For a distant observer, a clock near the black hole would appear to slow, as though each second were being stretched longer and longer. After crossing the horizon, moving toward the center becomes as unavoidable as moving into the next second of time. Turning around would not lead back outside, because every possible path points farther inward. And here, the picture becomes a little more unusual. Black holes have surprisingly few visible properties. In the simplest models, an isolated black hole is described by only mass, electric charge, and spin. Almost every other detail about the matter that formed it becomes hidden from outside observers. There is something quietly fascinating about this. Astrophysical black holes should be nearly neutral. Although electric charge is allowed mathematically, real black holes are expected to attract opposite charges from their surroundings and neutralize quickly. Mass and spin are therefore the main properties astronomers try to measure. After two black holes collide, the new black hole does not become calm immediately. Imagine dropping a stone into a pond. The water carries ripples away. In this case, space itself carries the ripples. For a brief moment, it vibrates, much like a bell after it is struck. Instead of producing sound, those vibrations send tiny ripples through space called gravitational waves. For a moment, consider what that means. The final vibrations reveal the new black hole's mass and spin. A heavier black hole produces a deeper, slower pattern, while its spin changes the rhythm. By measuring this fading signal, scientists can check whether black holes behave as Einstein's theory predicts. When two black holes merge, they release an astonishing burst of energy through ripples in space. For a fraction of a second, the power carried by those ripples can exceed the light produced by all the stars we can observe. The burst is not light, so our eyes would see nothing. Special detectors feel space itself stretch and shrink. And quietly, another curious detail appears. In 2015, LIGO made the first direct detection of gravitational waves. Imagine dropping a stone into a pond. The water carries ripples away. In this case, space itself carries the ripples. Two black holes had spiraled together and merged more than 1 billion years earlier. When the ripples finally reached Earth, they changed the length of LIGO's detectors by far less than the width of a proton. It may seem surprising at first. The first signal lasted only a fraction of a second. G 150914 swept through LIGO's sensitive band in a brief rising chirp. From that tiny distortion, scientists inferred the masses, distance, orbital motion, and final remnant. You can picture it for a moment. A merged black hole can weigh several suns, less than the two black holes that created it. Imagine dropping a stone into a pond. The water carries ripples away. In this case, space itself carries the ripples. The missing mass has not vanished. It has been converted into energy and carried away by gravitational waves, following Einstein's idea that mass and energy are two forms of the same thing. And here, the picture becomes a little more unusual. A merger can push the new black hole like the recoil of a fired object. Imagine dropping a stone into a pond. The water carries ripples away. In this case, space itself carries the ripples. If gravitational waves leave more strongly in one direction, the black hole is kicked the other way. A powerful enough kick could send it racing away from the center of its galaxy. There is something quietly fascinating about this. Some black holes may wander far from galactic centers. A recoiling remnant, a disrupted star cluster, or the merger history of a galaxy can leave massive black holes away from the nucleus. Astronomers search for unusual moving sources and displaced active centers. Pairs of supermassive black holes may create a very slow background hum across the universe. For a distant observer, a clock near the black hole would appear to slow, as though each second were being stretched longer and longer. Their ripples take years to rise and fall, so ordinary detectors cannot hear them. Astronomers instead watch extremely regular, dead stars called pulsars and look for tiny changes in the arrival time of their radio pulses. For a moment, consider what that means. A planned space observatory called LISA will use 3 spacecraft separated by millions of kilometers. It will measure extremely slow ripples in space that ground detectors cannot sense. This should allow scientists to follow massive black holes as they circle each other for months before merging. A small black hole can circle a supermassive one thousands of times before falling in. For a distant observer, a clock near the black hole would appear to slow, as though each second were being stretched longer and longer. Each orbit traces a slightly different path, creating a long and detailed gravitational wave signal. Reading that signal would be like using the small black hole to map the invisible shape of space around the giant one. And quietly, another curious detail appears. Stellar black holes are born from collapsing stars. When a sufficiently massive stellar core can no longer support itself, gravity can overwhelm pressure and trigger collapse. Depending on the star's mass and explosion, the remnant may become a neutron star or a black hole. Right off the bat, it might surprise you. Some black holes may form with little visible explosion. A massive star can collapse so completely that much of its material falls inward instead of being ejected in a bright supernova. Astronomers search for stars that simply fade away. You can picture it for a moment. A failed supernova may look like a star disappearing. If the collapse produces only a weak transient, the most dramatic evidence may be the absence left behind. Long-term surveys can compare old and new images to find massive stars that vanished. And here, the picture becomes a little more unusual. Black holes can be found through invisible companions. A dark object may reveal itself by pulling on a visible star. Astronomers measure the star's orbit and determine whether the unseen companion is too massive and compact to be an ordinary star. There is something quietly fascinating about this. Some nearby black holes barely feed at all. Gaia and other surveys have uncovered dormant candidates through stellar motion rather than bright X-rays. These quiet systems suggest that many black holes may be hidden in the Milky Way. The Milky Way may contain millions of stellar black holes. Only a small fraction have been identified because most are dark and isolated. Population models imply that the galaxy could hold vast numbers of unseen remnants. For a moment, consider what that means. Isolated black holes can bend background starlight. A lone black hole passing in front of a distant star can act as a natural magnifying lens made by gravity. The background star brightens, and its apparent position shifts, allowing astronomers to estimate the lens's mass. A black hole can steal gas from a companion star. The two objects circle one another, like dancers on an ever-tightening floor, losing energy until the final collision. In an X-ray binary, a black hole's gravity pulls material from a nearby star. The gas forms a hot disk and may flicker powerfully as it falls inward. And quietly, Another curious detail appears. Some black hole binaries switch states. The black hole itself stays dark, while the space around it behaves like a gigantic lighthouse, sending narrow beams far across the universe. The same system can alternate between bright, disk-dominated phases and harder states with strong, high-energy emission and jets. These transitions reveal changing relationships among the disk, corona, and magnetic fields. At first glance, nature appears to be breaking its own rules. Microquasars mimic quasars on a smaller scale. Nothing escapes as light from inside the black hole, yet matter just outside it can glow and launch narrow jets into space. A stellar mass black hole in our galaxy can produce a disk and jets moving close to the speed of light, resembling those around a supermassive quasar. Because the system is smaller, its changes unfold much faster. Think of the scene as though you were watching from a safe distance. The glowing disk around a black hole can produce echoes. A sudden X-ray flash near the center first reaches us directly. Then, some of the light bounces off the disk and arrives a little later. Measuring that tiny delay helps astronomers estimate the size and shape of regions too small to see directly. The scene becomes more unusual as we move a little closer. Iron in the hot disk can act like a marker. It produces a recognizable X-ray signal, but the black hole's gravity and the disk's rapid motion stretch and bend that signal. By studying its changed shape, astronomers can estimate how close the disk reaches and how quickly the black hole spins. This is the kind of fact that becomes more intriguing the longer you consider it. Hotspots may race around the edge. Bright clumps or magnetic structures can orbit in the innermost flow. Their changing light may provide a moving probe of gravity close to the horizon. A star does not have to enter a black hole to be destroyed. If it passes too close, the black hole pulls much harder on the near side than on the far side. The star is stretched, torn apart, and turned into a long stream of glowing gas. Follow the idea one quiet step further. A destroyed star can briefly awaken a quiet galaxy. The star is not swallowed in one clean bite. It is stretched into a glowing stream, with some material escaping and some beginning a final spiral inward. Debris from a tidal disruption event may form a temporary stream of falling gas that shines in ultraviolet light, X-rays, or visible light. A previously dormant black hole can suddenly reveal itself. Sometimes, the remains of a destroyed star help launch a jet moving close to the speed of light. The black hole is known by contrast, a dark center beside energetic beams that can travel for thousands of light years. If that jet points toward Earth, it appears much brighter, like a flashlight aimed directly at our eyes. These rare events allow astronomers to study a black hole that suddenly became active. That observation carries us naturally to another curious detail. A black hole can consume a neutron star. Gravitational wave detectors have observed mergers involving black holes and neutron stars. Depending on the masses and spin, the neutron star may be swallowed whole or torn apart first. It takes a moment for this possibility to settle in. Some mergers may create heavy elements. If a neutron star is disrupted outside the horizon, neutron-rich debris can power a kilonova and form heavy elements. If it disappears intact, the electromagnetic display may be faint or absent. Allow the picture to settle before we move on. There may be a gap in ordinary black hole birth masses. Stellar evolution theory predicts that certain massive stars can become unstable and leave few black holes in a particular mass range. Gravitational wave detections are testing where this pair instability gap truly lies. What follows gently reshapes the way we imagine the object. One merger produced an intermediate mass remnant. GW190521 involved unusually heavy black holes and produced a remnant of roughly intermediate mass. It offered evidence that the long-sought bridge between stellar and supermassive black holes exists. Its mystery comes from the contrast between a simple rule and an extraordinary outcome. Intermediate mass black holes remain elusive. Near the black hole, time would still feel normal locally, but a faraway observer would see the clock running increasingly slowly. Objects from hundreds to hundreds of thousands of times the mass of the Sun are harder to confirm than stellar or supermassive black holes. Candidates appear in dense star clusters, dwarf galaxies, and unusually bright X-ray sources. Dense star clusters may build black holes through repeated mergers. In crowded environments, stellar black holes can sink toward the center, pair up, and merge. A remnant, retained by the cluster, may merge again and grow in steps. There is more hidden inside that sentence than it may seem. A black hole can be older than its current galaxy. Galaxies assemble through mergers, carrying their central black holes with them. A black hole now sitting in one galaxy may have begun inside a much smaller ancestral system. The earliest quasars grew surprisingly fast. Astronomers observe billion solar mass black holes when the universe was less than 1 billion years old. Their existence challenges models of how seeds formed and how quickly they could feed. The picture becomes richer when one more fact is added. The first seeds may have come from giant stars. From a distant viewpoint, seconds close to the black hole would seem stretched, much like a recording played at an ever slower speed. One possibility is that the earliest massive stars collapsed into black holes tens or hundreds of times the Sun's mass. Rapid accretion and repeated mergers could then build larger objects. Nothing in everyday life quite prepares us for this. Some seeds may have formed by direct collapse. A clock near that intense gravity would appear sluggish to someone far away, even though it would feel ordinary beside the clock itself. Under special conditions, a huge, pristine gas cloud might collapse without first fragmenting into ordinary stars. This route could create a black hole seed thousands of times more massive than the Sun. Seen as a simple image, the idea becomes much less abstract. A black hole's own light can slow its feeding. As gas falls inward and becomes bright, the outgoing radiation pushes against new gas trying to enter. Under special conditions, however, thick flows can hide some of that light and allow the black hole to grow faster than the usual limit. This is the point where ordinary comparisons begin to fade. A black hole's appetite depends on its environment. A massive black hole can remain faint if little gas reaches it, while a smaller one can blaze when supplied efficiently. Brightness is not a simple measure of mass. The thought has a quiet pull of its own. Sagittarius. A star is unusually underfed. Our central black hole is massive, but currently faint compared with active galactic nuclei. Much of the nearby gas appears to be heated, stirred, or expelled before reaching the horizon. The Milky Way's center may have flared in the past. Structures above and below the galactic plane suggest that the central region experienced much more energetic activity millions of years ago. Sagittarius. A star may not always have been quiet. Allow that possibility to rest in the mind for a moment. Black holes can blow bubbles larger than galaxies. The darkness itself remains quiet, while the material caught nearby turns the surrounding space into a distant cosmic beacon. Jets and winds inflate enormous cavities in surrounding hot gas. X-ray and radio observations reveal these bubbles as records of past feeding episodes. They can prevent galaxy clusters from cooling too fast. Hot gas in galaxy clusters should radiate energy and cool, yet central black hole outbursts repeatedly reheat it. This feedback helps explain why the expected torrent of new stars does not form. Even this is not the end of the story. A black hole can move stars at thousands of kilometers per second. Stars orbiting near Sagittarius. A star travel at extraordinary speeds. Their precise paths provided compelling evidence for a compact mass of millions of suns. The result is unexpected, but the explanation is beautifully simple. One star completes an orbit in about 16 years. The star S2 loops around the Milky Way's central black hole on a highly elongated orbit. Tracking it has allowed astronomers to test relativistic effects near a supermassive black hole. For a moment, place yourself beside this distant event. Light from a star changes color slightly when the star passes close to a black hole. Strong gravity and high speed stretch the light toward the red end of the spectrum. Astronomers observed this effect in the star S2 near the center of the Milky Way, just as Einstein's theory predicted. The next detail changes the mood of the entire picture. A star orbiting close to a black hole does not repeat the exact same oval path. Looking in from a distance, an observer would see the rhythm of the clock soften and slow as it approached the edge. each orbit turns slightly. So over time, the root draws a flower-like pattern instead of one fixed ellipse. Astronomers have measured this slow turning around the black hole at the center of our galaxy. It is a subtle reminder that the universe does not need spectacle to be astonishing. A black hole can let us see the back of the glowing disk around it. Its gravity bends unsigned light from the far side, curving that light over and under the black hole until it reaches us. The result can look as though parts of the same disk are stacked above and below the dark center. Some light can loop around a black hole before escaping. The closer the clock moved toward the black hole, the longer each of its seconds would appear to last to a distant watcher. Light that circles once, twice, or even more times may create extremely thin rings inside the brighter image. Each ring is a delayed and distorted copy of the glowing material around the black hole. This small detail changes the way the entire scene must be imagined. The side of a spinning disk that moves toward us can look much brighter than the side moving away. This is similar to how an approaching siren sounds sharper than one moving away, except the effect changes light instead of sound. The uneven brightness is caused by speed, not necessarily by more material on one side. Black hole shadows can wobble. It is like finding the shape of an unseen hand by watching the brightness vanish around its fingers. Turbulent plasma changes from moment to moment, so the bright ring around a shadow is not perfectly fixed. Long-term observations can separate variable emission from the more stable gravitational outline. A further clue waits just beyond the first explanation. A black hole can have a temperature even though it is completely dark. It is rather like an unimaginably slow leak of energy. The loss is far too slow to matter during a human life, yet across immense cosmic ages, it can gradually change the black hole. Quantum physics predicts that space near the horizon allows a faint glow, called Hawking radiation, to escape. For real black holes, this glow is far too weak to detect, but it means a black hole is not perfectly black forever. This may feel unfamiliar, even within the already strange world of black holes. Large black holes are unbelievably cold. The process resembles a loss so faint that no human lifetime could notice it directly. Nothing noticeable would happen in our lifetime, but the universe has enough time for even this faint process to accumulate. Their predicted Hawking glow is colder than the faint background heat left from the early universe. At present, they absorb more energy from their surroundings than they lose, so they are not yet shrinking. The mind can follow it more easily through a gentle comparison. The smaller a black hole becomes, the hotter its Hawking radiation should become. Think of it as the quietest possible release, continuing across cosmic time. The change is almost absent on human scales, though over durations beyond imagination, it may eventually become decisive. A microscopic black hole would therefore lose energy much faster than a stellar one. Near the end, its radiation could become extremely intense, although no such tiny black hole has been confirmed. Here, a familiar idea gives way to something far less ordinary. Over an almost unimaginable length of time, Hawking radiation could make a black hole lose all its mass and disappear. Far from the black hole, an observer would see time near it unfolding more slowly than time beside their own clock. A black hole formed from a star would need vastly longer than the current age of the universe. Evaporation is therefore a prediction about the very distant future, not something happening quickly today. Even explained plainly, the idea retains a soft sense of wonder. Black hole evaporation creates a famous puzzle about information. Quantum physics says the information describing matter should never be completely erased. But if a black hole swallows matter and later evaporates as simple heat, where does that information go? Scientists still disagree about the answer. A strange calculation suggests that the information a black hole can hold depends on the size of its outer boundary, not on the amount of space inside it. Imagine storing everything inside a room on the room's walls instead of throughout its volume. This surprising idea began with the study of black hole heat and information. Take a moment to notice how unfamiliar that truly is. Even a small patch of a black hole's horizon can represent an enormous amount of hidden information. In simple terms, entropy counts how many hidden arrangements could produce the same object we see from outside. In physics, this amount is described using a quantity called entropy, which roughly measures how many unseen arrangements are possible. Black holes appear to pack more information into a region than any other known object. The holographic principle takes this idea even further. It suggests that everything happening inside a volume of space might, in some deeper description, be recorded on its outer boundary, much like a flat hologram can contain the image of a three-dimensional scene. This remains a powerful idea in theoretical physics, not a confirmed picture of everyday space. The deeper we look, the more delicate the mystery becomes. Some physicists have proposed that the event horizon may not be calm at all. Think of a boat drifting toward the lip of a waterfall, where the current finally becomes impossible to resist. As long as the boat has not crossed the edge, escape remains imaginable. Once the edge is behind it, returning is no longer one of the possible routes. It could be replaced by an extremely energetic layer, nicknamed a firewall, which would destroy anything crossing it. Other theories predict a smooth crossing, and there is currently no observation that decides between them. For a few seconds, the idea seems almost impossible to picture. Einstein's equations allow mathematical shapes that resemble tunnels linking distant regions of space. These are called wormholes. Ordinary black holes have never been shown to contain safe, usable tunnels, and keeping a wormhole open would appear to require forms of matter we have never observed. Picture the process happening slowly, almost frame by frame. There is no evidence that a real black hole is a doorway to another universe. We can measure how matter moves outside the horizon, but we cannot receive a message from anything that has crossed it. Portals belong to speculation and fiction, not to confirmed astronomy. And now, the scene reveals its most unusual feature. A white hole is a theoretical opposite of a black hole. To an outside watcher, the clock would seem to approach a pause, not because it had broken, but because gravity was shaping time itself. Nothing could enter it, while matter and light could only come out. The idea appears when some equations are run backward in time, but no confirmed object in the universe behaves this way. There is an unusual calmness to a process so far beyond ordinary experience. The Big Bang was not a black hole exploding. A black hole forms inside an already existing universe, while the Big Bang describes the early expansion of space everywhere at once. They can look similar in some equations, but they represent very different situations. Some theories suggest that black holes formed in the universe's first moments before any stars existed. If they exist, they would be ancient remnants formed before the first stars, drifting through the universe like fossils from its earliest chapter. Small regions that contained slightly more matter than their surroundings may have collapsed under their own gravity. These primordial black holes remain hypothetical because none has been confirmed. The deeper meaning emerges only when we give it a little space. Primordial black holes could make up a portion of dark matter, the invisible material that adds gravity to galaxies. Such objects would have been born near the beginning of cosmic history and preserved through time as traces of the young universe. However, searches have ruled out many possible sizes and numbers. They may still exist in limited ranges, but they cannot yet explain all dark matter with certainty. Ordinary black holes, left by dead stars, cannot account for all dark matter. That is important because a mysterious idea is not automatically the correct one. Observations must still survive every test. Astronomers have looked for the way compact objects briefly magnify background stars and have compared their effects with the early universe. The results show that there are not enough known black holes to provide all the missing gravity. Then another small surprise enters the picture. Black holes do not vacuum up the universe. Far from the horizon, their gravity behaves like the gravity of any other object with the same mass. If the Sun were magically replaced by an equal mass black hole, Earth's orbit would remain nearly unchanged, although sunlight would vanish. What happens here is far removed from ordinary experience. Black holes do not pull everything straight inward. An object moving sideways fast enough can continue falling around the black hole and remain in orbit, just as Earth continually falls around the Sun without crashing into it. Stars and gas can therefore circle black holes for millions of years. Consider the view without rushing toward the next detail. There is a final, safe circular path around a black hole. Outside it, matter can keep circling. Just inside it, even a tiny disturbance makes the orbit collapse inward. The position of this last stable orbit changes depending on how fast the black hole spins, and whether the matter moves with or against that spin. And now, after crossing these 100 strange ideas, we can begin to see why black holes continue to hold our attention. They are dark, but they reveal themselves through glowing gas, moving stars, bent light, and faint ripples traveling across space. They seem destructive, yet they can help shape galaxies. They appear simple from far away, yet they lead us toward some of the deepest questions in physics. Perhaps that is their greatest mystery. A black hole hides almost everything about itself, and still manages to teach us about gravity, time, light, matter, and the history of the universe. For now, there is nothing more you need to solve. Let those distant rings of light slowly fade from your mind. Let the stars become quiet again. And as you rest, remember that the universe can remain mysterious without becoming frightening. Sometimes, mystery is simply an invitation to keep wondering.